gas solutions are important as well. Let's look at the temperature dependence of solubility of gases in water. So gases generally have a lower solubility in water than ionic or polar covalent solvents. And this is not entirely surprising because most gases are nonpolar molecules, and nonpolar is unlike when you're looking at a polar solvent like water. If you have a gas that has solubility, you'll discover it's actually in most cases reacting with the water. And the reason you can push more into the water is because it's actually reacting into a new species when it is in the water. Something like CO2, some of it is actually reacting to form carbonic acid when it's in water. So for all gases, the solubility of the gas decreases as the temperature increases. So the hotter the liquid is, the less gas you can put in. So in this case, it's because the enthalpy of solution is exothermic, because you do not need to overcome solute-solute interactions. That's one less thing you have to handle. So you only have to worry about solvent-solvent and solvent-solute. So the heat of solution is generally exothermic for gases. And that is connected to the fact that the solubility of gases decreases, the temperature increases, which we'll revisit later. Thing where you'd see this, cold carbonated beverage versus a warm carbonated beverage. If you haven't chilled in the refrigerator, you're going to get a lot of the carbon dioxide coming out because the carbon dioxide is less soluble at higher temperatures. So try that sometime. Yeah, take 2 sodas, one that's been in the fridge and one that's been out, and pour them and compare. And that'll be an example right there of temperature dependence of solubility of CO2. So we talked about the temperature dependence on gases, but the pressure dependence is important as well. So the larger the partial pressure of a gas is in contact with the liquid, the more soluble the gas is in the liquid. And a good way to think about this is if you have a higher partial pressure of gas, you have more gas. There's more gas in that given amount of volume, right? Because PV equals nRT. And if there's more gas, then the rate of redissolving into the liquid will be higher. It will reach an equilibrium with more gas in the liquid. Again, going to soda is a great example. These are pressurized containers. And when you open the lid, then gas is released because you've lowered the pressure and you've changed the equilibrium so that the carbon dioxide can then come out. So that, think about it the next time you open a bottle of soda and think about what's going on. Okay, so a way to quantify this. So Henry's law is a measure of the solubility of a gas, and you can find that to a good approximation that when you're looking at low concentrations, and with gases you usually are looking at low concentrations dissolved in the solvent, then the solubility is directly proportional to its partial pressure. So the solubility is equal to some constant proportionality times the pressure of the gas. Here's an example of some Henry's law constant. Then this is called the Henry's law constant. This is Henry's law, and so therefore the constant is the Henry's law constant. It depends on both the solvent and solution. When you see tabulations of Henry's law constant, those are generally for aqueous solutions. So it'll be for aqueous solutions for a given gas. And so you can see we have some, they're usually quite small. There's one exception here we'll talk about in a second. So let's work through an example a little bit here. Let's do something quantitative. A lot of this has just been conceptual, but let's do some quantitative work. What's the concentration of nitrogen in the blood, of a diver at sea level, and at 20 meters deep? So let's assume the Henry's law constant for blood is equivalent to that of water. Blood is mostly water. So, so we would get that solubility equals KH. Let's just start at 1 atmosphere. And Henry's law constant for nitrogen is 6.1 times 10 to the minus 4. And it has units of molarity over atmosphere. And so 1 atmosphere, this is pretty straightforward. You would get 6.1 times 10 to the minus 4th molar nitrogen in the blood. So about 1 part in 1,000 of nitrogen. Okay. What happens ever at 20 meters deep? Now, there's one rule of thumb you don't have here, is that about each 10 meters, about 30 feet, is equal to about an additional 1 atmosphere pressure. So if you're at 20 meters deep, about 60 meters, then that is actually going to be about 3 atmospheres pressure. So in this case, it would be 6.1 times 10 to the minus 4th molar atmosphere times 3 atmospheres. And so this is going to be 1.83 times 10 to the minus 10 times 10 to the minus 3 molar concentration in the blood, about 3 times higher nitrogen, which, you know, that doesn't seem like a big problem at all. What happens if you swim up, you know, as fast as you can from 20 meters down, from 60 feet down in the water, which, you know, that doesn't seem that deep. Well, all of a sudden you have a blood solution of nitrogen that is supersaturated. How supersaturated? Well, we have, let's see how much blood is in a human body, about 5 liters of blood for an average adult. So how many moles of nitrogen is this? So we have 5.0 times, the difference will be, it'll be about 2 atmospheres worth of Henry's law constant, right? So it'll be about 1.22 times 10 to the minus 3rd molar times 50 liters. I'm just subtracting this number from this number to get 1.22 times 10 to the minus 3 molar constant. The differential, essentially how much extra nitrogen you have, how much above saturation, right? Because essentially it's 2/3 of the nitrogen is already is excess. You're only supposed to be able to have 1 of those. So now you have 2 of these, you know, spare floating around. So that ends up being 6 times 10 to the minus 3 moles of nitrogen in your blood that does not want to be in your blood. It wants to be gas. So how large a volume is that? Well, so at room temperature, let's say you're going up to the, you swim up to the surface, you have, let's just ballpark it that, you know, you know, you're probably in the Caribbean, maybe it's 30, 35 degrees or so. So maybe it's about 25 liters per mole of gas. 25 liters per mole times 6 times 10 to the minus 3 moles. So that would be about 6.3. This is about, so there's 25 liters per mole. 0.15 liters. So 0.15 liters. That's about half a Coke can of air. But remember, that's half a Coke can of air in your entire bloodstream. So that's, you know, what fraction of your blood? So that's 0.15 divided by 5.0, which is 0.03 over 1. About 3% of your blood volume suddenly decides, I want to be gas. And this causes some real problems. This is what's called the bends. You get all these nitrogen bubbles forming and are desperately trying to get out of your system. And it really hurts and can cause a lot of damage. Coming down from 60 meters, I think, I don't know, I can't remember exactly when it starts to be, go from you're going to be in bed for several days to you have a chance of dying. I think it's more like about 60 feet where it's you're going to be in bed for a few days recovering. So, you know, 3% of your blood essentially vaporizes. I mean, the blood isn't vaporizing, it's gas coming out. You're in trouble. So that is a demonstration of the importance of the pressure dependence of gases. So on that cheery note, that's the end of this lecture segment.